this case, we call that heater, and the transmission lines we have between the various instruments. Okay. All right. So let's look into the standard block diagram. This is a feedback control system. So we call that closed loop diagram. So if you notice here, for us to get the open loop transfer function from this current block diagram, we basically need to reduce the block diagram. Okay, reduce everything, and then we will come to a position in which everything will be in series. So GC, the GC, G valve, the G process, and so on, and also the transmitter will be combined in one single line, and we call that as open loop transfer function. If you notice, we have a negative feedback. So this feedback loop is directing to the negative negative system. So we call the negative feedback. All right. So let's look into the stability of closed loop control system. We have like the how to say the closed loop control system that we are referring is this one. So throughout this example, we'll be looking into sample of this only. All right. So looking at this, we also have set point and the output. So basically we can calculate the y over ysp from this case. Correct. So if you notice here, the y here is the control variable. So we need to control this by getting the signal from the transmitter. Okay. All right. So hue in this case is the manipulated variable, and this is the disturbance. And the P will be the control output, the output from this controller. So the P here is the control output, and E error can be calculated from the system based on this signal and this signal. So error basically can be calculated by finding the difference between the set point and the transmitter signal. All right. So everything else is very common that we have gone through in previous lectures. This is the controller transfer function. This is for final the valve transfer function, process transfer function, and transmitter transfer function. And this is disturbance transfer function. Now, if you notice the Km, okay, Km basically steady state gain for the transmitter, GM. Okay, so in this case, if it is a steady state, we can assume the GM equals to Km or Km equals to GM. Now, how we come to an analysis or conclusion that the closed loop control system is a stable one. So before going into the definition of what is stability and all that, it is very important consequence of feedback control is that it always can cause oscillation, right? So oscillation along the process. So we call that oscillation response. If the oscillation has a small amplitude, meaning if the oscillation, the amplitude here is small and damps out very quickly, then the control system performance is basically we consider that as a satisfactory or stable. All right. But then if under certain conditions in which the oscillation may be undamped or can even say have an amplitude that increases with, that means the fluctuation is there until a physical limit is reached. Okay, until it reaches certain limit, we called such a control valve being fully open or shut. Okay, the reason for the oscillation with higher amplitude difference is because of the control valve being completely shut or open. Okay, so under this condition, we call we say the closed loop system is very unstable. Correct. So our prediction or assumption, everything is going to be based on this condition. So let's look into what is the definition of stability. Stability means an unconstrained linear system is said to be stable if the output response is bounded for all bounded inputs. So what they mean by unconstrained here, okay? Unconstrained usually used to refer to the ideal situation in which there's no any physical limits to input. There's no physical limit on the input and output variable. So there's no constraint to the input and output variable. Now, if the output response is bounded, if they mention bounded, right? What is the meaning of bounded here? So we mean an input variable that stays within the upper and lower limits for all values over the time. So when it is bounded means there is a upper and lower limit. So it is lies within this boundary. All right. So this is the definition of stability. Now later we will also be looking into general stability criterion. So what is the meaning of general stability criterion? The feedback control system is stable if and only if all roots of characteristics equations are negative or have negative real parts. Okay. So what is the meaning of this? The feedback control system is stable. All right. So for that, we'll be looking into a root array situation in which we'll be looking into a graph. For a simple graph, let's imagine a simple x-axis and y-axis graph. Okay, x-axis and y-axis graph. If all roots of characteristics equation are negative or have negative real parts, okay, meaning that if it falls at this region, if you notice, this is a positive and positive axis, correct? So meaning we don't have any negative value, so we call that as unstable. Okay. If it falls here, we have at least one portion. We call that real parts as a negative value. So this is a stable system. All right. And if this portion, we also have a two condition mentioned here is satisfied, in which all the roots of characteristic equations are negative or have negative real parts. So this portion we call it as unstable. All right. Now, what they mean by characteristic equation. So this is the characteristic equation 1 plus GOL. Now, if you notice, the GOL means the transfer function for open loop system. So this is basically the multiplication of all the transfer function in a closed loop system, in a open loop system, which derive from the closed loop system. Okay, so from the system we will break all the loops and then make it as linear function, right? So here the GOL is the in function of the controller, valve, process, and also the transmitter. Now, when it comes to characteristic equation always will be equals to 0. So meaning 1 plus, in this case, all the GC, GV, and GP will be expressed as KC. KV will be KV over tau RS, tau VS plus 1 times with the process gain over the tau PS plus 1. And then for the transmitter, Km over tau MS plus 1. And this is entirely equals to 0. All right. So if you notice here the tau RS plus 1, tau PS plus 1, tau MS plus 1 are the roots. So if all roots of characteristics equation. So this is the characteristic equation and their roots are the tau Vs plus 1 and so on. So if these roots are negative or have negative real parts, the system is stable. All right. So when in another term, we always express that in terms of A plus B J, right? So if this is negative, then the system is stable, we call that. All right. All right. So this is the characteristic equation that they gain from the previous diagram that we look into the feedback loop control system, right? So here they already mentioned closed loop. So for them to make it open loop, it has to be 1 plus GOL equals to 0. So this is the characteristic equation and they equate it as 0. And the GOL it will be the GC, GV, GP, and GM equals to 0. And in this case, the roots of the characteristic equation will be S minus PI, and we need to determine the types of response that occurs. So here, the complex roots usually will have oscillatory response, and all roots in left half of complex plane are negative. What they mean by complex plane is the one I explained just now with the x and y axis, right? So all roots in left half of complex plane will have negative or have negative real parts. So we call that as stable system. All right. So this is the complex plane that we mentioned just now. If it falls at left hand side, stable, and right hand side means unstable. All right. So here, if you notice, 1 plus GOL equals to 0 for the characteristic equation. S roots at this point are positive. So they have positive, S roots are positive. Okay, so positive real, they have, we can conclude that they have the positive real part. Our requirement is to have negative real parts, right? So for example, A plus BJ and A minus BJ. So if you notice the real parts here, the A and A in both cases are positive. Okay, so this is what they mean by positive real parts. So this graph, or we call that complex plane, basically provides a graphical interpretation of the stability criterion. So we have to take note on the positive roots and the negative roots to justify whether the system is stable or unstable. Basically, qualitative effects of these roots on the response of closed loop system will be like this. Okay, so like if we look into each location of this point, if it is here, it has real part. Okay, but negative real root. So we call that as stable. If it falls here, we call that as positive real root. Okay, so the system is unstable. So if it is stable, means it is already reaching a stable condition at this point. Okay, unstable means it keep how to say, exceeding or increasing in terms of. So this is unstable. All right. So if looking at these two positions, okay, both have a complex roots and negative real roots. So as time goes on, the fluctuation is reducing. So we call that as stable. And if looking into positive real parts, we call that how to say, unstable. This system is unstable because the fluctuations is increasing. The amplitude of the oscillation is increasing. So the condition is the system is stable if and only if all roots of the characteristic equation must be negative or have negative real parts. Okay, otherwise we call that as an unstable system. So the roots of the characteristic equation here is not as we looked just now, right? So consider this example. We have a process GP equals to 0.2 over negative S plus 1. That is open loop unstable. Okay, unstable. If GV equals to GM equals to 1, determine whether proportional controller can stabilize the closed loop system. Now, if it is a proportional controller, meaning the control system here will be transfer function will be equals to the controller gain. All right. So the characteristic equation for this system is starting from the basic one, 1 plus DOL must be expressed in terms of GC is expressed in KC. Okay. GP is given as this, and GV and GM is almost equals to the unity. All right. So they replace that. Right. Something's wrong. So they replaced that, and then they got all right. So they replaced and they got negative S plus 1 plus 0.2 Kc. So rearranging the roots, you will be getting S in terms of S. Okay, so our aim is to find out what is the root, right? So also for the for the stable system, we assume 1 plus GOL 1 plus GOL equals to 0. So the entire thing will be equals to 0. So 1 plus GOL equals to 0, which is 1 plus 1 plus GC, GP, GV, GM equals to 0. And here the 1 plus and so on is expressed as 1 plus KC. All right. And this entire term will be expressed as 0.2 right? 0. Negative S plus 1 times 1 times 1 equals to 0. So rearranging the equation, finally you will get S equals to 1 plus 0.2 Kc. Now, okay, so if you notice the roots, the root or the roots of the closed system will be less than 0. So here also same case must be less than 0. All right. So for us, in order to conclude or to determine whether proportional controller can stabilize the closed loop system or not, okay, we have to identify first. For this system to be stable, S must have a negative value as less than 0. So when you are equating the entire equation as 0, you will be getting the Kc value approximated roughly or false at which range, right? So in this case, solving will give you negative 5. So the stability requirement is that Kc less than negative 5. Okay, if Kc less than negative 5, this example shows that feedback controller can be used to stabilize the process. Okay. Now, here if Kc less than negative 5 means they also mean negative Kc less than negative 5. So it depends how the Kc value is projected. Now, looking into the root stability criterion, we have earlier we have looked into stability criterion only, general stability criterion. So now we have root stability criterion. So when it comes to root stability criterion, what is root stability criterion? They have given a characteristic equation in this form instead of the 1 plus GOL equals to 0. So at this criterion, the characteristic equation will be equals to 0. All right. So all of the coefficients, meaning this one must be positive. Okay. And if any coefficient is negative or 0, then at least one root of the characteristic equation lies on the right on the complex plane here, and the system is called the unstable. All right. So their equation only when it comes to the criterion, their equations same, different, and analysis or the conclusion will be similar. All right. Now, root array is how they projected the information from the complex plane in a row and column form. Okay, the first two rows of the root array comprise of the coefficients in the characteristics equation, meaning these two. All right. The elements in the remaining rows are calculated from coefficient by using the formula. All right. So row 1, row 2, row 3, row 4. And we have the coefficient from the equation as an minus 1, b1, and so on up to the n plus 1 term. All right. So here the rest of the term can be calculated. How? If you notice, this is actually minus 2 of the earlier column, correct? So an minus 2 will become an minus 2. Here minus 2 will become minus 3, all right? And here minus 2 will become minus 1. But when it comes to B and C term, we don't perform this calculation. Here it will be B1 and B2 and C1 and C2 and so on, D1 and D2. Only these two will be calculated, okay? Using the coefficients from the formula, of course, right? So the root stability criterion is a necessary and sufficient condition for all roots of the characteristic equation to have negative real parts. Okay, similar to our general stability criterion in the left column of the root array are positive. All right. So let's look into this example. Determine the stability of a system that has the characteristic equation. So characteristic equation is given here. All right. All right. So we need to express everything in terms of S term, right? So if you notice here, S4, S3, S2, and we need to have S1, all right? S1 is S to the power of S1, but the S is not expressing here, meaning their coefficient is equals to 0. The coefficient in front of the S is equals to 0. That's why it disappeared already. And then S to the power of 0, this is 1, this is 0, will be the 1. All right. So everything need to be expressed in terms of S term. All right. So because the S term is missing, its coefficient is 0. Therefore, the system is unstable because we need from the root stability criterion, we must have a positive coefficient in front. Correct? So its coefficient is 0, so it doesn't fall between. It cannot be categorized as positive or negative. So the system is unstable. This is an example how we analyze the root stability criterion. Right. Next example, find the values of controller gain KC that make the feedback control system with the following transfer function stable. All right. So if you notice here, they have given us GC, GV, GP, GD, and GM. All right. So for the stability criterion, we know the 1 plus GOL equals to 0. Okay. So the GOL here is GC, GV, GP, and GM equals to 0. All right. So 1 plus GC is the KC. GV is 1 over 2s plus 1. Everything expressed in terms of their roots, the s. All right. So GV is done. GP is 1 over 5s plus 1 and 1 over s plus 1 equals to 0. So rearranging the equation, you'll be getting 2s plus 1, 5s plus 1, s plus 1 plus kc equals to 0. All right. All right. So expanding further, you'll be coming to this position. Okay, expanding everything, you'll be coming to this general form of root criterion. So if you notice, their coefficients, everything is positive. So we can construct the root array. Okay, so how to construct a root array? From the basic equation, we list down on the left hand side, we list down all the coefficient there. Okay, for the B1 and C1, we leave it as it is. But then for the first two, 10 and 17, we take from here. And then the 8 and 1 plus Kc is from the following term. So we take the 8 from the term and 1 plus Kc from the next term. All right. So here B1 will be B2, C1 will be C2. So in order for this system to be stable, B1 and C1 must be positive also. Okay, because everything has to be in stable form, right? So how to calculate the B1? We have a formula earlier. This A, okay, AN minus 1, AN minus 2, the multiplication of this minus the multiplication, the multiplication of this minus the multiplication of this over multiplication of AN minus 1. All right. So if you notice, in this form, the multiplication of this 10 and 1 plus Kc minus 17 and 80, 17 and 8. So the B1 can be calculated as 17 and 8 minus the 10, 1 plus Kc. All right. And over the n minus 1. All right. 70. So this must be more than 0 because our coefficient must be positive, right? So more than 0. You can actually solve this equation, but then we don't have the Kc value. So we assume everything is more than 0. So 17 times 8 will give you 136 minus 10, 1 plus Kc more than 0, 10, 1 plus Kc more than negative 136. All right. So 1 negative 10 minus 10 Kc more than negative 10, 136. All right. So negative 10 Kc more than, if we solve plus here negative, so bring to the other side will become negative 126. All right. We have negative sign here, so we're going to make it as positive. We're going to change the sign here to earlier more, now less. So negative 126 over negative 10. So Kc is basically 12.6. Right? So if you notice, the Kc here is a positive value, so we can say the system is stable. All right? Okay. So the system will be stable if Kc falls between -1 and 12.6. This one the formula that we did here is for B1, but you have to do for C1 also. So if it falls within these two ranges, we call that the system will be stable. All right. Right. So next example, suppose a control system is modeled by GP, GP equals to GD 8 plus S plus 2 to the power of 3, GVGM equals to 1, GC equals to KC. Okay, we need to find the highest value of KC for a proportional controller for which the system is stable. All right, using the root array. So the stability criterion for the system will be 1 plus GOL. The characteristic equation will be 1 plus GOL equals to 0. So here 1 plus GC, GV, GP, GM equals to 0. So 1 plus KC, GC equals to KC, GV given as 1, GP is 8 over S plus 2 to the power of 3, okay, times the GM as 1 also equals to 0. So if you notice here, the S plus 2 term as the rule, all right? So the S plus 2, we can solve the entire equation, rearrange the equation as equals to 0. So by from here, we expand to this, okay? This is the general, how to say, root array standard form of equation, right? So from here, we extract the coefficient at this in front of all the S term, all right? So we have 1 and 6, 12 and 8 plus 8 Kc, all right? So we express these two and these two extract from the equation, all right? And then we calculate the B1 as difference between multiplication of the diagonal term, all right? And then divide with the 6. And for C1, we can calculate using the equation, all right? So if we solve each, both also has to be more than 0, okay? So it falls within the -1 and 8. If you notice, 8 is the Kc must be less than 8. Okay, so the highest or the maximum value it can reach is 8. So we can say the process is stable. All right. All right. So we have another, other than the general stability criterion and also the root criteria, stability criterion, we have another paid approximation, we call that. So if, but this one, how to say, not that important, but then for your knowledge also, if characteristic equation is not a polynomials, the root criterion is not directly applicable. Okay, what they mean, what they mean by that is not a polynomial. Meaning, if let's say we have an equation in terms of e to the power of negative theta s. Okay, we can approximate the system as 1 minus theta over 2 over 1 plus theta over 2s. Okay, so now the definition of the entire pad approximation depends on the theta value. If a polynomial approximation to e to the power of negative s is introduced as given here, this approximation, then we can use the root criterion to determine the approximate stability limits. All right, as long as to the power of exponential to the power of s term is given, then we can use the root criterion. So this is the PET approximation that they mentioned. Now, let's look into this example. We have a feedback control system with GC equals to KC, GV equals to 2, GM equals to 0.25, and GP is given in terms of exponential term. Find the range of KC values that will yield a stable closed loop system. All right. So where do we start from? We need to come out with the characteristic equation first. 1 plus GOL equals to 0. So we have given as the GV, GC, GV, GP, and GM equals to 0. So when you rearrange or replace everything, GV is 2, GP is 4e to the power of negative x over 5s plus 1. Okay. And GM here is 0.25 equals to 0. All right. So if you rearrange this equation, you'll be getting 1 plus 2 Kc over 5s plus 1 times 1 minus 0.5s over 1 plus 0.5s. Why? This term, if the expression is in terms of exponential to the power of negative s that we saw in the previous slide, that can be expressed in terms of 1 minus theta s over 1 plus theta s. All right. So equals to 0. All right. So we can solve this. 5s plus 1, 1 plus 0.5s plus 2 Kc, 1 minus 0.5s equals to 0. All right. So we'll be getting equation in terms of 5s plus 0.5s plus 1 plus 2.5s squared plus 2 Kc minus Kcs equals to 0. So this is in the general form that we want. But if you notice, the Kcs and the 0.5s can be gathered together. So we can rewrite this equation 2.5s squared plus 5.5 minus Kcs plus 2 Kc plus 1, okay, equals to 0. So everything is in terms of S, right? So we can group that 2.5 and here will be 5.5 minus Kc. And here will be 2 plus, 2 Kc plus 1 and here will be equals to 0. So by performing the root criterions, root stability criterion, and here will be B1 and C1, right? So we basically can solve the entire equation, all right, by using the formula to calculate the B1 and B2, all right? So from here, we will be getting at the final equation as 5.5 minus Kc more than 0 and Kc. So here Kc will be less than 5.5. This is one portion. Another portion which we'll be getting 2 Kc plus 1 must be more than 0. So Kc must be more than negative of or we call that more than negative 0.5. All right. So if you notice here, the range here is between the 0 for the KC is for the KC is between 5.5 and negative 0.5. All right. So this is the KC range that we got just now. All right. So this is basically about how to calculate the KC range. Now we have another example here with the evaporator, okay, used to concentrate a dilute solution of a single non-volatile solid, okay, non-volatile solid in a volatile solvent by evaporating solvent using heat supplied by a steam coil. Okay, so steam coil is this one we are talking about. Three process variables can be manipulated. The PS, steam pressure, okay, product flow rate, vapor flow rate of solvent D. The product composition XB can be measured on line. So the question is, should each control valve be fail open if fail close? Justify or justify your answer. It is not if or. Okay. Should each control valve be fail open or fail close? We need to justify the answer. But before that, what is steam control valve function? If fail close means close to prevent preheating, overheating of the evaporator. Okay, meaning the level control valve fail close means to maintain certain level, but then it fail. So if the level is too low, the steam coil will be exposed to vapor and could lead to the coils to burn out. All right. So that is for the control valve, level control valve, and also the steam control valve. Now, if it is a pressure control valve, it is a fail open, means to prevent over pressurization of the evaporator. All right. So this is what they mean by fail open or fail close. All right. So if we have the similar process diagram here, right? So we have this concentration controller here as the product concentration of this XB, okay, increases. We want the steam pressure PS to reduce evaporation process. Okay, this is the signal given to the pneumatic valve here. All right. So this is about concentration controller they are talking about. So by that we can reduce the evaporator since the steam valve is failed to close. Okay, when the evaporator is failed, steam valve is failed to close. Okay, so meaning the controller output signal at this portion, the controller output signal to control valve should increase to increase PS direct acting. All right. If the steam valve failed to close, okay, steam valve failed to close means the controller output signal giving signal to the control valve must or should increase to increase the PS steam's pressure. All right. So this is about the example. So if another question, the part B of this, should each PI controller be direct acting or reverse acting? We need to justify that also. All right. So for a pressure controller or pressure, pressure PI controller, as the pressure, as the liquid, as the pressure level increase here, as the pressure increase, we basically want to want the solvent flow rate to increase as well. Okay, so that it can balance itself. since the control valve is failed to open. If it doesn't open, meaning the controller output signal to the valve must decrease. Okay, so with that we call it as reverse acting. All right. So whether it need to be direct acting or reverse acting is the most suitable type. So the corrective actions to reduce the pressure by increasing the flow rate must be taken. So that is the purpose of reverse acting lah. All right. So it must work both way so that it can how to say adjust the level accordingly. Doesn't matter pressure or level controller or even the pressure controller. Okay. So you can have a look at the all the examples provided. So with that, we are done with today's lecture. I think I have given, have attached the tutorial 10 part A solution already in the my times for last week's lecture one. So make sure you all have a look at it. Very important for your final. And today's one partially, yes, coming out. So like it or not, you have to focus on all. All right. So with that, we are done for today. Any question? No question? Okay. Send me your attendance here. All right. Okay. I think attendance I can take from here, lah. No issue. No need to send. Okay. All right. See you all during your tutorial time.